Hello and welcome to this talk about service broker integration with Kubernetes operators. So first a short introduction. My name is Julian Fischer. I'm CEO of a company called Anynines. We are focused on designing, building and operating application developer platforms. As part of that mission, we also have a group of products managed as well as distribution, including Cloud Foundry, Kubernetes, and data service automation. So the anynines data services is basically the group of automation products that led to the topic of this conversation. So these anynines data services, they cover the full life cycle of all those data services. And by automating the life cycle of that many data services, it is quite natural to confront all those obstacles in automation, as well as those integration challenges we are talking about today. So yes, the data service automation with Cloud Foundry, we have plenty of experience of automating data services with BOSH, and are now adding support for native Kubernetes deployments. And therefore, the on-demand provisioning of dedicated data service instance is and has been a topic that has basically made up our implementation effort for quite a long time. For those who do not know the term, on-demand provisioning means that whenever an application developer requests access to a certain service instance, the service instance will then be on-demand deployed, for example, by using BOSH to deploy a virtual machine, or then Kubernetes to deploy pods using a stateful set and services and so on. So in general, the idea is that there's a service broker. The service broker is, for example, integrated with Cloud Foundry, and that upon the request of an application developer, an automation is triggered, in this case Postgres service broker, and it creates a single Postgres, in this case represented by a virtual machine. Or another service instance could be represented by 3 virtual machines comprising a streaming cluster, for example. The architecture that enables such an on-demand provisioning in our case looks as follows. A Cloud Foundry client creates a service that triggers the cloud controller, which then triggers the service broker, which implements the service broker API, creates a deployment manifest to what we call the deployer, which prepares BOSH deployment manifest or a Kubernetes resource specification and passes it on to the corresponding backend, which will then deploy the actual service instances. So the idea of this talk is to think about the question, how do you integrate service brokers with arbitrary operators? So given that there is a Kubernetes operator and you want to have service instances created using that operator within your Cloud Foundry environment, how would you do that? And if this is possible, might it be even possible to create such a service broker with generic capabilities so that arbitrary operators can be implemented? Which leads to the question is, how generic should such a service broker become? And that's one of the few questions we are going to look at in greater detail now. So first of all, let's have a look at the building blocks. So for those who are not as familiar with Cloud Foundry and its the way it integrates services, then this chapter is for you, as well as for those who do not have in-depth knowledge about Kubernetes operators. So if you have ever seen Cloud Foundry from an application developer perspective, you may have encountered the Cloud Foundry command line, where you have the option to list all the data services or services in general that are available in the Cloud Foundry by using the CF Marketplace command. Now, in that architectural draft we're going to develop throughout the talk, you can see that the application developer can use services from that marketplace and invoke the create service command or create service binding command respectively, which will then be communicated to the Cloud Foundry's Cloud Controller, where the endpoint of the Cloud Foundry API is being made up. The Cloud Controller in turn talks to the service broker. So that leads to the question, what is the Service Broker API? It's an open standard, and as the name suggests, it allows the creation and management of services. It's not really very in-depth determined what such a service is. In the context of this talk, we are talking about data services such as databases, message queues, analytics servers, and so on. So the terminology introduced by the Service Broker API comprises three important concepts: a service plan, a service instance, and a service binding, where service instance and service binding are the most important terms. A service instance is basically what that entity that you want to provision, for example, a database. In the context of on-demand provisioning of dedicated data services, a service instance is likely to be a virtual machine or a group of virtual machine, and in Kubernetes respectively a pod or a group of pods. The service binding represents the connection between the application and the corresponding data service instance. It could be, for Postgres for example, be a dedicated database user. The service plan is a group of settings that determines the nature of the service instance. For example, the service plan could say I'm a small solo instance, or it could say I'm a large clustered instance, where the solo instance maps to a single virtual machine or a single pod with only 4 MB of memory, where 4 GB of memory, where the large clustered instance refers to 3 nodes, 3 VMs or 3 pods in a stateful set with 64 GB of memory each. All right, so the Service Broker API, the Open Service Broker API, is pretty much straightforward. It defines an endpoint for retrieving metadata that describes what the service is about and which service plans are available. It allows the creation and update of service instances as well as their destruction, and the same for service bindings. All right, so once a service broker implements the Service Broker API, it is possible to create service instances and respectively service bindings. So it is possible to create a database server or cluster, and it's possible for an application in Cloud Foundry to connect to that cluster by getting a service binding to it. Now, if we want to make this if we want to make an integration with Kubernetes Operators, it's meaningful to have a short view and short look into what Kubernetes Operators are about. So the Operator SDK is basically a framework that allows creating 2 different kinds of Kubernetes resources more easily, which is a custom resource definition as well as its corresponding controller. So CID, a custom resource definition, is a Kubernetes construct, and it may look like this. You can imagine this custom resource definition as a generic, or as a description of a data structure that you want to teach the Kubernetes API. So that means in this case we have an object that's called pgs.ds.anynines.io, which is basically describing how Postgres instances could look like. we can see that this data type defines an attribute called replicas, which is required, and that there are further properties, including the Postgres version, which is of the type string. The default would be the version 12.2. There's also an attribute called replicas of the type of integer. So the namespace scope means that this particular object or objects of corresponding to this customer resource definition can be created within a namespace. And the names for these objects will be PGs in plural and PG in singular, and the kind, that's the term you will use in the specification, will be PostgreSQL. All right, now once you have taught Kubernetes that trick, that custom resource definition, you can create objects of this kind. And in this case, you can see it would be a very simple Postgres object specifying the variables we've earlier defined here, the Postgres version and the number of replicas. Now, to sum it up, a custom resource definition is basically a user-defined type that can be taught to Kubernetes. And what you get from that is that Kubernetes will, for you, create an endpoint to store objects of your user-defined type, both providing the endpoint as well as the persistent storage by storing it in its internal etcd store. So it's basically like a service broker where it provides you the endpoint to store the objects, the service instances, so to say, you want to create. You can store them by creating them using that API Kubernetes will offer you using the kubectl command, and you can also retrieve them. However, what it doesn't do, it doesn't implement any behavior. Custom resource definition is purely defining a data type, and you will have to register a corresponding controller which implement and listens to events of your particular custom resource type, and then consequently act upon it. So a controller will be watching a primary resource, in this case, for example, your Postgres objects, and it will then subsequently translate it into so-called secondary resources. In this very simple memcache example, the primary resource would be a memcached object, and in the secondary objects would be a pod. In our Postgres example, it is the primary resource would be a Postgres object after that accepts the two attributes replicas and Postgres version, and will translate it more likely into secondary resources such as a service as well as a stateful set. A controller here, using the Go operator SDK and implemented in the Go language, implements a reconcile loop and responds to changes of the underlying custom objects. In this case, what it does, it takes the memcache object as the desired status has been specified by the user, looks up whether such an object already exists, and if not, translates it into creating the secondary resources. In this case, this would mean creating a pod. As I said earlier, in a Postgres example, this would more likely be creating a service and then a stateful set. But the structure is similar. The controller basically owns the translation from the desired state of the primary object and writes specifications of the desired state of the secondary objects. So as I said, it reads custom resource object specifications and translates that from primary resources into secondary resources. It will also watch those primary and secondary resources for change. So for example, in Kubernetes, when you specify a stateful set and you manually delete a pod, then the stateful set controller will recognize that and recreate a pod of similar identity. And analog to that, your controller, let's say taking care of your Postgres or Memcache resource, will also have the chance to listen to changes of the secondary objects. For example, if your stateful set or your pod has been deleted, you could take corrective action in the controller and recreate them. So, all right, now we know about the Service Broker API. We know that the Service Broker API offers service plans, service instances, and service bindings. We know that custom resource definition teaches Kubernetes about new data structures, for example, Postgres objects. And we know that controllers would be used to translate those custom types into secondary resources that already exist within the cluster, for example, services and stateful sets. So in order to get an exemplary draft, the service broker integration with operators needs to be put into some kind of architecture. So the first step for this would be to look at the Open Service Broker API and think about the required integration work. So if you look into how to get the metadata from the Service Broker API, like the catalog, which would enumerate the services that are offered by the broker, as well as the service plans, you could provide in a Service Broker implementation that based on the custom resource definitions that come with your operator. For example, this could enumerate configuration options offered by the Postgres instances the operator will allow you to create. If your specification on the operator side is more flexible, you can still define service plans in the service broker by grouping certain parameters together so that they will, make up a service plan. The create service instance operation of the service broker API will then map to create such an object specification, similar to the Postgres specification we've seen earlier, and pass it on to the operator. However, by default, there is no corresponding object in Kubernetes and most of the operators that is similar to service bindings. So if you don't have anything that represents a custom resource definition or some other API that allows you to create, let's say, a Postgres user, the service broker would not be able to create a Postgres user and therefore not be able to create a service binding. So this is a problem we'll have to look into. But first things first, let's talk about how would you do a service instance? How would you create a service instance in particular? So there's also the problem, how would you update an instance? But as we've limited in time, we'll stick with creating service instances for now. So the main idea would be that once you've uttered the desire to create a service instance, for example, by executing a CF create service, you'd be trying to combine these request parameters from the create service request that will end up in your service broker with attributes read from the service plan. So for example, if you create a Postgres instance single of the service plan single small, the service plan will eventually resolve into the fact that it is represented by one virtual machine or one pod, and that For example, the memory is about 4 gigabytes and not 8 or 12 or 16 or whatever. So yes, service plan, you will boil this down to generate a deployment specification. And then once you have that deployment specification, which is the Postgres specification we've seen earlier, for example, the operator, you will pass this on to the operator. And the operator in turn will then translate that into its secondary objects, for example, a stateful set. Now, a stateful set is already a Kubernetes native resource, so that will then be handled by the Kubernetes API. But there's basically nothing that prevents you from stacking operators hierarchically in a chain of responsibility. So you could basically create a Postgres object, for example, that translates into 2 more elementary operator resources, still controlled by your or one other operator. So as I said earlier, the CF create service statement here for Postgres, single small, an instance called PG instance, here with the custom parameters, activating a plugin for Postgres, will be turned into an HTTP request containing the parameters provided, which would include the service plan GUID. So the service broker internally will resolve that into the specifics of the service plan, and eventually here the service plan is represented as a YAML specification, and you can also see that it points to a certain VM type and persistent disk type. As this YAML specification here in the service broker is taken from an example where Bosch virtual machines are being deployed, we still have to resolve some cloud properties, which won't be necessary when dealing with Kubernetes operators, I assume, because you don't have to interface with infrastructure APIs directly. But it's basically the same job. So the service broker will still have to look up the service plan and resolve it to the attributes underlying the service plan. In the Bosch example, this will basically go down to the AWS instance types, which then maps to CPU and memory. So in Kubernetes examples, you would do that mapping directly by giving away a pod or stateful or pod template resource descriptions about CPU and memory. So it all boils down to that the service broker collects the information provided in this create service request, and it enriches this information by retrieving information from the service plan and eventually create a data structure that contains all information necessary to construct the actual service instance. Now, when looking into the integration with operators, all we have to do is creating the object specification. So the service broker's main job will be to collect the data and then write out such a service specification. So what it basically does, the CF create service command to the left will eventually create the specification for the Postgres object shown on the right, which is a little bit more complex than our earlier example, but you get the point. Now, once we have created such an object specification, we can pass it on to the operator, and the operator will do its job, resolving it to secondary resources, a service, a stateful set, and let Kubernetes do the job. But we have to think about the service problem, the service binding problem for a second, because in many operators, there's no functionality that can be addressed by creating custom resources that will then create a user for you, and that's a problem. And as Kubernetes doesn't have anything either, we need to think about that. So service bindings are unknown to Kubernetes and are unknown to most of the operators I've seen, and therefore it needs to have some thought. So let me share a exemplary design draft with you. In this case, you can see there's a create service command uttered by a Cloud Foundry application developer. You can see him at the top. There's a cloud controller that will listen to that request and pass it along to a registered service broker. In this case, it's an anynine service broker for Postgres. In our particular architecture, the service broker is generic. It is independent from the underlying data service. So the service broker is configured to be a Postgres SQL service broker. It is not programmed to be one. And the data service specifics are implemented in an adapter class that we call the SPI, the service provider interface. And in this case, this is configured with the Postgres SPI, obviously. This architecture has been implemented in the context of our on-demand provisioning with Bosch and can still be used with Kubernetes, where there's a component called the deployer that reads all the information and translates it into a object specification. So what you can see here is that the Kubernetes deployer creates these object specifications, and kubectl applies it to the Kubernetes API. Well, this is not necessarily a kubectl command. It could also be building a Go data structure and passing it on to the Kubernetes API directly without kubectl, as without invoking a process. But you get the idea. In our Bosch architecture, we'd be using a different deployer, which would then talk to the Bosch API respectively. But the point here is that if you look into the Kubernetes API, then or below the Kubernetes API, you will see that it is not Kubernetes that carries out the creation of the Postgres service instance, but the respective controller. So first of all, the Kubernetes API knows about our Postgres instance object because we've created a custom resource definition for it. Now, the service instance itself will be created by the corresponding controller in its reconcile loop. Now, if there's a create service binding request, that in our architecture would be the responsibility of the Postgres SPI, because, for example, in Bosch, you have a similar problem. Bosch doesn't know anything about service bindings. So we have to look up the service instance that we have created in the service in the CF create use case, and then we have to create a Postgres user manually. Now you could repeat that and apply a similar logic with Kubernetes, but I don't think it is really a good choice for Kubernetes, because we want to also support Kubernetes application developers who would not use the service broker, but use the custom resource definition in operators directly. So it may be more wise to create a custom resource definition for a service binding and have a controller reconcile that. Now you could again have the CRD controller talk back to your service broker and then trigger the SPI. But the question is, who in this architectural diagram should be the leader? We do have the integration already between the SPI and the service broker. So for us at anynines, it would be very easy to leave the SPI the primary actor in the system. But we decided to go 100% Kubernetes native, and therefore let the controller create the service binding. The service binding in this case, a Postgres user will then either create a Kubernetes job that would eventually will utter Postgres commands against the particular service instance, and offer the abstraction of creating such a service binding, again as a custom resource definition. So all the SPI in Postgres has to do is create another specification, in this case for the service binding, and the rest will be reconciled by the operator. Now, in this architecture, this enables a Kubernetes app developer using those custom resources directly without the service broker API and manage Postgres instances without a Cloud Foundry. This would be necessary and useful if there is no Cloud Foundry in a certain Kubernetes environment, for example. And still, the service broker can beautifully integrate the operators into a Cloud Foundry. Now, the service broker is generic to that point that it makes assumptions about the lifecycle events covered by the service broker, as well as its syntactical structure. But it does not depend on a data service directly, other than there has to be a little adapter at this point, which eventually, I think, can be refactored so that it won't be necessary. Now, we should also mention that if you want to keep that service broker implementation simple, you should maybe restrict the Kubernetes application developer to modify a service instance that is owned by a Cloud Foundry application developer. Because the cloud controller stores metadata and the service broker eventually or possibly stores metadata, it could be leading to inconsistencies if a Kubernetes application developer were to modify that service instance. Well, let's say at least unless you make that communication bidirectional and somehow try to reflect changes with using the Kubernetes API back into the service broker API, which to me appears unnecessary complex and also maybe not very clean, because basically you have to talk back to the cloud controller, and that's a very ugly mixture or mix of the responsibilities. So the most simple approach would be to leave the a service instance to either in the hands of an application developer in Cloud Foundry or an application developer using Kubernetes, but not mix the two for a particular service instance. They both can create service instances though. So should a Cloud Foundry Kubernetes user be able to modify a certain service instance? No, definitely not. If you want to keep it simple, if you want to go down the route and enable that, it is possible, but it may be more effort. Let's sum it up. A service broker integrating arbitrary operators, it may be possible, as we've shown with our generic service broker, but if you really want to make it entirely generic, then the question is, can you make those assumptions about the operator and how the specification of a particular operator will look like, how it will implement the service, the particular service's lifecycle. If there's, for example, no backup API, then you wouldn't be able to support backups. If there's no functionality for service bindings, well, you wouldn't be able to support service bindings, which would make the integration incomplete. So you have to make certain assumptions about the operator to be integrated, to make a generic service broker work and to make it economically viable. Because if in the end the service broker is so much about generic mapping, about uncertain data structures in the operator and the unknown cover of use cases, then you might be ending up in a very meta service broker where you don't know anything about the structure, and you'd be ending up configuring a lot. And at some point, the generic service broker would be so much meta programming code that it just became, economically uninteresting to implement it. So the more homogeneous the functionality and the syntax of your operators are, the easier it will be to have a generic service broker. The operator must provide functionality that can be used to implement service bindings. If not, the service broker needs an operator-specific service binding extension. So this is what we call the SPI in the earlier diagram, which would be a plugin to the service broker that knows how to create, for example, a database user. And the service broker will be much simpler if a service instance is either under the control of a Cloud Foundry application developer or a Kubernetes app developer. So I hope you've learned about how to integrate Kubernetes operators with Cloud Foundry using service brokers. If you have any questions, just feel free to reach out or ask your questions in the Q&A section. So thank you very much for your time, and speak to you soon.